Students are able to see the screen share? Everybody are able to see the screen? Post in the chat box. Okay, fine. Okay, so let us discuss about that is coordination compounds. So in today's we will discuss this coordination compounds and we will have some objective questions. We will do objective questions. Okay. So bonding and coordination compounds. So first of all, here uh, this coordination compounds, it starts with that is theory called Werner's theory. We started in theory called Werner's theory. This theory gives idea about that is structure of complex compounds. It gives idea of the structure of the complex compounds, right? Just a minute, student. Okay, it gives that is idea of the that is structure of the complex compounds. Okay, so what is this Werner's theory states? So there are two postulates are there for Werner's theory. So metal atom possesses two types of valences. One is we are calling it as primary valency, other we are calling it as secondary valency. So this primary valency we are calling this as that is oxidation number. This primary valency is equals to the oxidation number. So the primary valency of metal is equals to the oxidation number. And here this primary valency is satisfied by that is which type of that is negative ligands is satisfied by negative ligands. Okay, so here this primary valency is nothing but it is equals to oxidation number of the central metal ion, and it is satisfied by the negative ligands. And secondary valency, it gives the coordination number. Okay, a metal atom tends to satisfy both the primary as well as secondary valencies. Secondary valence is satisfied by ligands are directional. Okay, while primary valence is satisfied by negative ions are non-directional. So you have to make a note that is secondary valency are satisfied by ligands are that is it is are of directional. This is directional. Okay, and whereas that is while the primary valencies are satisfied by negative ions are non-directional. Okay, fine. Next, what are the limitations of Werner's theory? So if you see the limitations of Werner's theory could not explain that is complex forming property. So why the metal atoms, metal ions will form complexes with ligands? Okay, so it doesn't explain this phenomenon. Okay, the complex forming properties of only certain elements only it is explained, but it doesn't explain for all elements, for all metal ions of the D block elements. Next, Werner's theory could not explain about directional characteristics of bonds. It doesn't explain about the directional characteristics of bonds. Next, it doesn't explain about that is characteristic magnetic and optical properties of complexes. Why some complexes are able to show that is doesn't explain about that is characteristics property, that is magnetic characteristic as well as optical characteristic properties of the that is complexes. Fine. So because the complexes are, that it is able to show both that is magnetic properties as well as the optical properties. So it doesn't explain this. Next, let us go for the next screen share. Fine. Next, valence bond theory. So in order to that is explain the demerits of Werner's theory. So what are the limitations of Werner's theory? That limitations. Okay. So that limitations of Werner's theory are explained by the valence bond theory. Okay. What does Werner's theory didn't explain? In Werner's theory, whatever the points which doesn't explain, that was explained by the valence bond theory. Okay, let us see the postulates of valence bond theory. So here, first of all, before going to valence bond theory, so what does it describe? It describes the bonding in terms of hybridized orbitals. Okay, valence bond theory, that is, it will valence bond theory. It is explaining. It will explains the that is bonding in terms of hybridized orbitals. Okay, so by valence bond theory only we can explain the bonding. Okay, in the complexes, hybridized orbitals of central metal atom. Fine. Next, or ion. It explains, moreover, it not only explains the bonding, it will explain the shapes of complexes also. So what is the geometry of the complexes? This valence bond theory also will explain the that is shape of complexes and relation between the observed magnetic behavior and bond type. Okay, relation between the observed magnetic behavior and bond type also it will explain. Next, postulates of valence bond theory. So let us discuss the postulates of valence bond theory. So what are the postulates of valence bond theory? The central metal atom or ion makes that is the central metal atom or ion makes available number of vacant orbitals equal to its coordination number which hybridize together. So here, you know that if you are taking that is complex compound. So in complex compound, you can see metal ion. That metal ion will be that is having a bond with the ligand. Okay, and it is having some charge, right? So here, the central metal atom ion makes available number of vacant orbitals equal to its coordination number. So how many vacant orbitals are there? That will be the coordination number. Okay, suppose if the metal ion is having the 5 vacant orbitals. Okay, so that means it can accommodate 5 ligands. That means it can able to form bond with the 5 ligands. That is the first postulate. The second postulate, the vacant hybrid orbitals form coordinate bonds with ligands. Vacant hybrid orbitals form coordinate bond with the ligands. Yes. This bond are of equal strength and directional in nature. Okay. So all the that is all metal ligand bonds are having the that is suppose if you are taking that is a metal atom and a ligand. So suppose I am taking a metal atom and it is having a that is associated with the 5 ligands. So all these 5 bonds. Okay. Okay, all these 5 bonds are of having the equal in strength and they are directional in nature. And here we have a list of compounds here, hybridization and geometry of complexes. So this table will explains that relationship between the that is coordination number and type of hybridization and type of hybridization and geometry of the complex. Right. So here, if you see this one, if the metal atom that is complex is having coordination number 4, if the complex is having the coordination number 4 means, so either the metal ion may undergo sp3 hybridization or it may undergo dsp2 hybridization. That means total coordination number 4 means it is that is 4 number of orbitals are participating. Okay, 1 s orbital and 3 p orbitals, and here 1 d orbital, 1 s orbital and 2 p orbitals. Suppose if the type of hybridization is sp3, okay, if the type of hybridization is sp3, the geometry of complex, what we are going to get tetrahedral. Example that is you can take that is this complex, that is nickel tetracarbonyl NiCO4. This comes under this tetrahedral shape, right? Next, square planar. So square planar means the type of hybridization is dsp2. It is also having the coordination number 4. So which type of complexes will show that is square planar complexes means that is nickel. Okay, nickel as well as nickel which is having +2 oxidation state, and platinum which is also having +2 oxidation state also will show. Example you can take that is a nickel, that is tetracyanonickelate. Tetracyanonickelate. Okay, this one, and as well as you can take that is tetramine platinum, that also you can. This also will show that is our square planar geometry. Next, if you are taking that is hybridization geometry of complexes. If coordination number is 5 and sp3d hybridization, it is having the trigonal bipyramidal. If that is coordination number is 6. Again here also you can see if coordination number 6 means if it is having sp3d2 hybridization means it will show octahedral. And if it is having D2 sp3 also, it will show the octahedral. Okay. For sp3d hybridization, what is the shape we are going to get? That is trigonal bipyramidal. The shape of the complex is trigonal bipyramidal. So example, the example you can take, that is it's a nickel atom is having, that is oxidation number +3, pentacyanonickelate. So it will show that is trigonal bipyramidal. Okay, that is this one, this complex NiCN5. Okay, 3 minus. It will comes under the trigonal bipyramidal. One more example also you can take. That is you can take that is copper CuCl5 copper complex, which is having the, that is oxidation state, that is +2. Okay, CuCl5 3 minus. So it will show that is trigonal bipyramidal. Octahedral. Okay, octahedral means many octahedral complexes we have. That is hexamen cobalt 3 complexes. Okay, cobalt complexes. All this we can get the octahedral complexes, D2sp3 as well as. Now coming to the, that is limitations. What are the limitations of valence bond theory? So here also this valence bond theory is also having limitations. So what are the limitations of the valence bond theory? Let us have a look of the limitations. So the limitations of valence bond theory. See here, if you are seeing, it could not explain the, that is color property of the complexes, as well as it could not explain about the, that is electronic spectra of complexes. Okay, valence bond theory, it is able to explain about the bonding as well as shape, but it doesn't explain about the, that is color as well as the electronic spectra of the complex. Next, it could not explain the structure of the, that is this copper complex. Okay. Next, it could not explain why the pairing of electron occurs in the presence of strong ligands. Okay, so you know that pairing of electrons will take place. So when strong electrons, strong ligands are approaching the metal ion, so what happens means the unpaired electrons are going to get paired up. So it doesn't explain why the pairing will take place. Pairing of electrons will takes place in the presence of the, that is strong ligands. Okay, so this is the, that is limitations or demerits of the valence bond theory. Next, let us go for the next screen share. That is, in that next screen share, we are going to explain. Okay, next we will go for the, that is crystal field theory. Okay, now I will share the, that is crystal field theory. Students, are you able to see the screen? Crystal field theory. Please message in chat box. Are you able to see the screen or not? Because just now the connection has went off. You see whether the crystal field theory, are you able to see on the screen or not? Message in chat box. Okay, fine. Let us go further. That is crystal field theory. So this theory, why it has put forward, because in order to explain the, that is whatever the, that is disadvantage, whatever the, that is valence bond theory is not explained. So in order to explain, this crystal field theory has put forward. After some years, this crystal field theory has put forward. Okay, let us discuss about the, that is in this crystal field theory. In this crystal field theory, according to crystal field theory, under the influence of ligand field, degeneracy of d orbitals is destroyed. So, what do you mean by that is degeneracy? Degeneracy of d orbitals. Degeneracy means, so the term that is degeneracy means degeneracy. Degeneracy means it is having same energy. Having same energy. This we are calling it as degeneracy. Okay. So degeneracy means having same energy. So according to crystal field theory, under the influence of ligand field, degeneracy of d orbitals is destroyed. So you know that when metal ion, okay, when ligand is approaching the metal ion, when so in the last class also I said that I have shown the diagram. So when the metal ion is approaching the ligand, see here I will be showing this one. So when the metal ion is approaching the ligand, you know, first this all these d orbitals are having the same energy. Okay, all they are having the same energy. So this is the state when the metal ligand is far away from the metal ion. When the metal ion is approaching the ligand, okay, or sorry, when the ligand is approaching the metal ion. So So what happens when the ligand is approaching the metal ion? So the repulsions will take place between the this metal ion as well as the ligand. Just a minute. Just wait a minute. Okay. Okay. Now, if you see this, when the ligand is approaching the metal ion, so what happens because of repulsions? You can see here the energy of the that is 5 d orbitals has been raised. Okay. Now the metal ion. Okay. When the ligand is approaching the metal ion, so what happens means this degeneracy is removed. That means before the ligand is approaching the metal ion, all the 5 d orbitals are having the same energy. All the 5 d orbitals are having the same energy, right? When all the d orbitals are having the same energy, when the ligand is approaching, what happens very closely? So when the distance between the ligand and metal ion will becomes less, at that time what happens is the degeneracy of the d orbitals are removed. That means the d orbitals will split into two. The d orbitals are set up into two set of orbitals. Just a minute, students. Fine, students, are you able to see the screen? Now, are you able to see the screen? See, students, are you able to see the screen or not now? Once you check, are you able to see the screen or not, students? Message in chat box. You are not able to see the screen? Right. Now, students, message in chat box whether you are able to see the screen or not now. Screen is visible or not? Not visible? Now it is visible, right? Okay, fine. See, now you can see that is d orbital is that is okay. D orbital is d orbitals are split into two set of orbitals. One we are calling it as T2G orbitals. This we are calling it as T2G. T2G means triply degenerate, and this we are calling it as EG. EG means doubly degenerate, right? And so there exists and that is energy gap between the T2G as well as EG orbital. So this gap we are calling it as crystal field stabilization energy, CFSE energies we used to call. Next, coming to the that is octahedral complexes. In octahedral complexes, you can see somewhat different situation. So here also, before the ligand is far away from the metal ion, you can see all these d orbitals are having the same energy. So when the ligand is comes that is towards when the ligand is approaching towards this metal ion, what happens is so there is a slight increase in the energy level of the d orbital. D orbitals. Next, when the ligand is coming still very close towards the metal ion, and because of the interactions. Okay, because of the interactions between that is metal ion and ligands, the d orbitals are splitted. Here also the d orbitals are splitted. The d orbitals are splitted into two set of orbitals. Okay, one we are calling it as EG. EG means doubly degenerate, and other is called T2G. T2G means triplet degenerate. So here, how the metal ion will approach the that is ligand. So you know that metal ion will approach the ligand that is in two possibilities. So here I will tell you how the metal ion will approach the ligand. Just a minute. So here the metal ion will approach the ligand in the two ways. Either the metal ion may approach the ligand that means along the axis, or either it may approach between the axis. Two possibilities are present. Okay. So I will show that one, how the metal ion will approach the ligand. See here. So this is the metal ion. This metal ion, that means ligand, so it can approach, so it is x-axis. This is an x-axis, or you can take this as y-axis, this as x-axis, and this you can take it as z-axis. So here the metal ion is present here. This is a ligand. So the ligand can approach the metal ion by two ways. Either the ligand may come between the axis, or it may come along the axis. When the ligand is coming along the axis, so we are going to get which type of splitting means octahedral splitting. What type of splitting we are going to get? Octahedral splitting. Okay. Suppose if the ligand is approaching, that is, this is second way, this is first way. First is octahedral splitting. So if it comes along the axis, if it is coming between the axis, the ligand is approaching the metal ion between the axis, which type of splitting we are going to get? That is tetrahedral splitting. Tetrahedral splitting. Okay, octahedral splitting as well as tetrahedral splitting. So now, so what is the difference between octahedral splitting and tetrahedral splitting? In octahedral splitting, you can see the d orbitals will split. In both cases, the d orbitals will split into two set of orbitals. If you are taking the octahedral splitting into consideration, so here the d orbital will split into two set of orbitals like this. In that you can see that is Eg orbitals will be having more energy compared to the T2G orbitals. So this is T2G. T2G orbitals will be having less energy, and Eg orbital will be having the more energy. This is which type of splitting? Octahedral splitting. Octahedral splitting. Fine. Suppose if you are taking the reverse case, if d orbitals are, that means if the ligand is approaching the metal ion in the second path. Okay, so now in this case you can see that d orbitals will split into two set of orbitals. In this case, the T2G orbitals will be having the more energy, and Eg orbitals will be having the less energy. That means that is that is 5 d orbitals are present, dx5, dy, dzx, dx1 minus y square, and dz square orbitals. So in this 5 d orbitals, so 3 d orbitals are having the lobes. That is, this is that is okay. This is dxy. Okay, so this is the orbitals which is having between the axis. The lobes will be, and for that is dx square minus y square and dz square orbitals. This is the that means orbitals will be that is along the axis. Okay, so like that you can, so the theory behind what is how the splitting will take place. Okay, now let us go for the next screen share. Okay, so now the degeneracy is removed. Now you can see this one. Next, spectrochemical series is there. What is spectrochemical series? Spectrochemical series means, so this series will tell us about that is the strength of ligands. This series will give us the strength of ligands. So here we have arranged the ligands in the increasing order of their strength. Spectrochemical series will give us the what we are going to get the idea of the strength of ligands. By spectrochemical series, by looking at the spectrochemical series, so we can make out which ligand is having more strength and which ligand is having the less strength, and we can have a comparison between the strength of two different ligands. Okay, so you can compare by looking at this series. We can compare the ligand field strength. We can compare the strength of two ligands. Okay. Fine, students. See here, which is strong ligand among this? That is, CO is a strong ligand. This is strong ligand, which is placed at the right side of the spectrochemical series. And I minus is very weak ligand. It is very weak ligand. So based on spectrochemical series also, you will get some questions. So based on the spectrochemical series, there is a chance of asking questions on this topic, spectrochemical series. So how the question they will frame means based on the spectrochemical series. So they will ask which of the following. So they won't give the full order, right? They won't give the full order. So they will break this series into 4 parts, and they will say that among this which order is correct. Okay, so they will give, that means they will misplace the positions of the ligands, and they will ask, so which order is correct. So here if you see this spectrochemical series, first one is I minus, next to Br minus, next to sulfide and thiocyanate. So here first I minus is present, iodide ion, I minus, next Br minus, next sulfide, next thiocyanate. Okay, you can make this as the first part. And next chloride, hydroxo, oxalate. This you can make into second part. What is this one? Cl minus, okay, F minus, OH minus, and oxalate, C2O4 2 minus. This you can take it as second part. Fine. Next you can take that is H2O, aqua, H2O. Next NCS minus, okay, isothiocyanate. Next NH3. Next En, ethylene diamide. Next last one is NO2, Cl minus and CO. Okay, so this you have to remember this. Very important. Based on this, you will get this one. You will get question based on this one. See, I will write once again the series. Okay, so this is about the spectrochemical series, and here this spectrochemical series, what does it gives the idea? This is also very important. Crystal field stabilization energy. So it is having the CFSC, we used to call it as. Here they have given. See this one. Increasing order of CFSC. Okay, what is this CFSC? Crystal field stabilization energy. So here this CFSC, it depends upon on what factors this CFSC will depend. Okay, so here CFSC will depends upon, that is oxidation state of central metal ion. Very important. CFSC depends on oxidation of central metal ion. CFSC, it depends upon the oxidation of central metal ion. Okay, so here how it is related? So here it is related that crystal field splitting is directly proportional to charge on central metal atom. Directly proportional to charge on central metal atom. Okay, that means more charge is there. more CFSE is there. Suppose if I am taking two metal ions, I am comparing the CFSE energy. One is having +2 charge, other is having +3 charge. Among these two, which is having more CFSE? This one is having more CFSE. Okay. So the crystal field stabilization energy of this metal ion, which is having +3 charge, is more. Why means here I said so crystal field stabilization energy is directly proportional to charge on central metal ion. So here, if that is oxidation state is more, so it will have more CFSE value. If more CFSE value means, so I will show you here. Suppose this is one set. Okay, this is, we are calling it as CFSE energy. Now you see this one, the energy gap between, that is EG orbitals and T2G orbitals. Here it is less. So this crystal field splitting energy is due to M2 plus ion. Suppose if M3 plus is there, so M3 plus ion crystal field stabilization energy, let us discuss. For M3 plus ion, we will be having more energy like this. Okay, this is EG and this is T2G. This is crystal field splitting energy for that is M3 plus. For M2 plus, the stabilization energy is less. The splitting will be less. Okay, because I said that CFSE value depends upon the charge on central metal ion, EG and T2G. Now you can see this. Compare these two. So where the energy gap is more, in which diagram? The second diagram, that is the energy gap is more. So the energy gap is more means what does it means? That it is having more CFSE value. More CFSE value. Why we got means because it is having more, that is charge on the central metal ion. Here we have, that is less CFSE value. Why we have less CFSE value? We have because it is having less charge. Okay, so as I said that the CFSE is directly depends upon the charge on the central metal ion. Okay. So this is the and Jahn-Teller distortion effect is there. And here two more points you can see. If delta, that is crystal field, is less than the pairing energy. Okay, this we are calling it as pairing energy. Okay. If a crystal field splitting energy is less than the pairing energy, then the complex is high spin complex. If a crystal field splitting is more than the pairing energy, okay, then the complex we are having it is low spin complex. And we have Jahn-Teller distortion also. This is Jahn-Teller distortion is nothing but it is an asymmetrically filled ligands. So I will, Jahn-Teller distortion. Distortion means a change in shape. What you are calling it as change in shape. So here, if you are taking the Jahn-Teller distortion, so I will tell. So if you are taking the octahedral complex, if you are taking the octahedral complex like this, okay, you are taking an octahedral complex. Here you can see the metal ion. Some internet connection problem is there. Okay. Let me explain. So I am taking the octahedral complex. Okay. So here this is ligands are the octahedral means how many ligands are the 6 ligands are there, right? So in this 6 ligands, so if you see this one, that is in this 6 ligands, this we are calling it as equatorial. This we are calling it as equatorial, and this we are calling it as axial. So axial bonds we are calling this as, and these bonds we are calling it as equatorial bonds. These ligands are the equatorial position, and here the bond length for, if you are taking the bond length, so for axial, if you are taking the axial bonds, and this we are calling it as equatorial. There is some internet connection problem is there. Okay. So axial metal ligand is having the more length compared to the equatorial. Okay, so this we are calling it as Jahn-Teller distortion. Okay. Now I will show, that is, I will share the screen. There you can see some MCQs. These MCQs. Question number 19, 20, 21, 22, 30, 31. Take 5 minutes time and complete these questions. First question is based upon the, according to Lewis theory, what does the ligands are? Ligands are classified as. Okay. Second one, ligand in a complex salt or. Next, the third one, 21st one, the ligand, that is, uh, this is, we have the ligand ethylene diamine. Sorry, ethane, this is, which type of ligand they are asking. 22nd one, an example of ambidextrous ligand is. Students who has missed previous classes, you will get recorded videos of that class in. Okay, you will get recorded videos of that class in. That is, we'll have, that is, in chemistry bulletin. You can visit in this YouTube, this one. Okay, friends. So you will get in YouTube. There is a channel called Chemistry Bulletin. In that you can see the previous recording classes. Okay. In YouTube you will search Chemistry Bulletin. You will get that previous recording classes. Now is the question of 32, 33, 34. What is the answer for question number 19? 19 here. What is meant by Lewis basis? Okay. So here ligands. ligands will comes under the, that is Lewis acids or Lewis bases. Ligand is a, that is a metal atom or ion or molecule. Ligand is a metal atom or ion or molecule which can donate the pair of electrons. Okay, so how the ligand is defined? Ligand is nothing but it is a, that is a species. It is a species which, it is a species which can donate a lone pair of electrons. Which can donate lone pair of electrons. Okay, what is ligand? It is a species which can donate lone pair of electrons. So it might be a molecule. Ligand may be a molecule, or it might may be atom, or it might may be ion, which is having the ability to donate a lone pair of electrons. So according to Lewis theory, if a species is donating a lone pair of electrons, that species which comes under Lewis acid or Lewis base. It comes under the Lewis base. So it is basic in nature because of donating electrons. Next, 20th question, ligand in a complex salt R. So, ligand in a complex salt R. So here it is anions linked by coordinate bonds to a central metal atom or ion. Cations are linked by coordinate bonds to a central metal atom or ion. Molecules linked by a coordinate bonds to a central metal atom or ion. Okay. So here that is ions or molecules that is linked by coordinate bonds to a central metal ion. So option is D is correct. Okay. Next, the ligand. Okay, here they have given this ligand. So this is comes under which type of ligand? Okay, so this if you are taking this ligand, ethane diamine, tris ethane diamine, this ligand we are calling it as. Yes, here you can see a pair of electrons on the nitrogen. Here also you can see a pair of electrons on the nitrogen. So outside one nitrogen is present. So this ethane amine. Okay, this is ethane amine. So this ethyl amine is, how many are there here? 3 are there. So each that is ethane amine is having how many electrons? Only one pair of electrons. Okay, each ethane amine is having only one pair of electrons. So total how many that ethane amines we have? 3 are there. 3 plus 1, 4. So 4 means it is comes under tetradentate. Next, an example of ambidentate ligand is an example of ambidentate ligand. So which is the example of ambidentate ligand? You can see this one. Okay, an example of ambidentate. Ambidentate means it can donate from the, that is front side atom as well as the back side atom also. That means ambidentate. That means it can coordinate from the two sides. Okay, it can coordinate from the two sides. Example, that is Cn minus. You can have that is Cn minus as well as Nc minus. You have ambidentate ligand. Cn minus as well as Nc minus. Okay, so here if you take amine. Amine means it is having the formula NH2. Okay, next aqua. Aqua means H2O. It is not ambidentate. It is also not ambidentate. CloroCl minus. No, it is also not ambidentate. Thiocyanato. Yes, Nc minus. We used to call this one. It is an ambidentate. That means it can coordinate to the metal ion. This we are calling it as ambidentate ligands. Fine. So this we are calling as ambidentate ligands. Next, 30th one. Which ligand is expected to be, that is bidentate? Which ligand is expected to be bidentate, which is having less donor atoms? So here this is monodentate. Bi means only one lone pair of electrons. This is monodentate, and this is also monodentate because it is also having only one lone pair of electrons. It is also monodentate. And this one C2O4 2 minus. This we are calling it as, what is the name of this ligand? Oxalato. It came from the oxalic acid. Okay, this is an oxalato ion, CO minus and CO minus. Next, okay, and O2 is a monodentate ligand. So what about 33rd question? O2, it comes under which dentate of ligand? It is bidentate ligand. It is a bidentate ligand. Okay. Next, I will show the next screen share. Just to take the screenshot for that one. Please take the screenshot because time is over. Please take the screenshot of this one. As the following type. Okay, one more screenshot also I will show you. I have taken a screenshot. Next, one more also. Take the screenshot for this one also. Okay, take the screenshot for this one. Okay, students, I'm leaving the meeting because time is over and moreover some internet connection problem is there. Okay, so I'm leaving the meeting, students. Time is over. Okay.